Alright, welcome to video 3 of Unit 8. This one's kind of an introduction to rate laws. We'll talk about actually finding them later, but first, you gotta actually learn what in the world a rate law is. I will tell you, this is kind of the main concept of pretty much all kinetics, whether you go AP, whatever, it all comes back to rate laws. So, try to pay attention. An equation that directly relates the rate of a reaction to the concentration of its reactants is called a rate law. Basically, the rate law tells you how fast a rate will go based on how concentrated we have our reactants. Now, we're going to be using things, and you're going to get the impression that they're really easy to find if you have data. And that's true, but it's often hard to find that data. If you have a rate law, though, for, let's say, you're developing a new medicine to take away headaches faster. If you have a rate law based off all the reactants, you can quickly figure out how to make this medicine take place faster, or maybe even last longer. It's super useful for rates. It can, if you're trying to make a fire go faster and you can somehow get an idea of a rate law, you can figure out what you can do to make it faster. May even turn out that some of the things that you've been adding aren't going to make it go any faster. So they're crazy useful. Rate laws consist of 3 parts: reactant concentrations, reactant orders, sometimes just called rate orders, and rate constants. Now, before I go on much farther, let me show you what a rate law tends to look like. We're going to go into this more, but this is a basic rate law. Typically, it all equals the word rate, and that just represents the rate of a reaction at really whenever they have these specific concentrations. Okay, refers to our rate constant, and we'll come back to that. But for now, all you got to know is that's just basically some number that basically just makes everything work. Bracket A and bracket B represent the concentration of each reactant, and the exponents they have represent what we call our rate orders. They represent how strongly that reactant affects the rate concentration. So the higher actually the exponent or the order, the more it actually affects it. So, all right, there you go. Rate laws are based off the concentration of reactants, not products. Please keep that in mind. They're not based on how fast a reaction will go based on how fast you're measuring products. That really doesn't help you. That'd be like saying a reaction goes as fast as it goes. It's not helpful. It's based off reactants, whatever you're actually putting in it. And again, typically those reactants concentrations will be based by writing the substance's formula in brackets, just like before I had A and B both in brackets. Those represent the concentration of those reactants. The reaction orders, sometimes we call rate orders, and I see them both. They're both as common. Half the time you'll see reaction orders, half the time you'll see rate orders. They both mean the same thing. These are the exponents associated with the concentrations of each reactant. So we'll talk very soon about what the different exponents means. But again, they overall deal with how strongly the rate depends on the concentration of that individual reactant. The higher the exponent, the more the concentration of that reactant affects the overall reaction rate. So a order of 2 is stronger than an order of 1, which is stronger than an order of 0. We actually can't have order zeros. You normally don't go much higher than 2, but if you did, it'd be stronger than 2. Reactants commonly have one of 3 orders: 0, 1, or 2. Now, when you get to higher levels of chemistry, when you start looking into actually kinetics, this is honestly kind of false. You can have orders all over the board. They could even be negative or fractions. Most commonly, though, they will be either 0, 1, or 2. Just know they don't have to be. So a reactant with an order of 0 is called a 0th order. One with an order of 1 is a first order reactant, and one with an order of 2 is a second order reactant. I know that may seem mildly obvious now that I've shown you, but you're going to see those terms like something about, oh, it's first order with respect to blah, blah, blah. That means that thing's first order, which means it has an order of 1. So let's talk about, though, what these orders actually mean. A 0th order will not affect the reaction's rate at all. So you can put 2,000 percentage of your original amount of 0th order reactant, and it's not going to go any faster. Okay, it's just not going to happen. It doesn't change it. It may be involved in the overall chemical equation, but just having more of this for some reason does not make anything go faster. A first order reactant, though, will change the reactant's rate, but it changes it corresponding to its actual change in concentration. We're going to talk about this in just a second, but basically this means if you double your concentration, your rate will be doubled. If you triple it, it'll be tripled. First orders, to me, make the most sense, because whatever you do to them, your reaction directly changes. Again, if the first order reactant's concentration is doubled, then our rate will be doubled. If its concentration is cut in half, like it doesn't always have to increase, then our rate is cut in half. It's just whatever we do to our concentration, we do to our rate. So that also means, and what you're typically going to see, is if you find some reactant the rate is directly changing with it, like you find that we doubled this reactant and our rate went twice as fast, that means that reactant is first order. Most of your work will be finding the orders, not quite finding the changes. But first orders, again, they make the most sense. So 0th order, don't do anything. First order, change based on whatever you do to them. Second order, they change corresponding to the square of its change in concentration. Okay? This means that if I double something, my rate will be times 2 squared, so to the 4th. If I triple something, it'll be times 3 squared, which is to the 9th. So it's squared, the rate will change corresponding to the square of our change in concentration. Again, if our reactant order's concentration is doubled, which means times 2, then our rate will be quadrupled, which is 2 squared. If it's tripled, then our rate will be 9 times as fast. If we cut it in half, if our concentration is cut in half, then our rate will be 1/4 as slow. So we're basically just squaring the change to get our change in rate. All right, so 0th, don't change it. First, change directly. Second order changes according to the square. All right, please keep in mind, though, they cannot be determined just from a balance equation. They have to be determined off experimental data. Now, I'm not going to ask you to find it off balance equations. There's probably a question on your test that says, can they be found from a balance equation? No. I've seen that all the way up to AP Chem tests. It's one of those questions that you're like, really? Like, stop asking me. They may look like they relate. Please just realize that is complete coincidence. Just because the coefficient happens to be 2 and the rate happens to be 2, that's not related. Currently, it actually kind of is related, but we'll get there later. But for now, they're not related. Lastly, a rate law involves a rate constant. That is a specific number that is per reaction that represents how fast the reaction will go. Typically, you're not given this. What you do is you solve for your rate law and basically just take the numbers from one of the trials and plug them in and solve for it. It basically deals with how fast a reaction goes. So the larger reaction constant, the faster it is. So if it's large, meaning times 10 to the 5th or something bigger, it's going to be pretty fast. If it's, times 10 to the negative 5th, it's slow. So that's your rate constant. All right. So we got a little practice. Suppose our initial rate for a first order reaction is 0.5 molarity per second. Now, I'm not dealing with rate laws yet. I'm just giving you some practice with the rate. So our reaction overall is first order, and it's an original rate, it's 0.5. What will be the rate when half of that reactant remains? So we're assuming there's just one reaction and it's first order. Okay, when half of it remains. And what will the rate be when 1/4 of it remains? All right, take a bit, try to find the actual rate. Come back in a bit. All right, so for A, we have a first order reactant, and if we cut it in half, then we're going to change it by 1/2 to the first power because it's first order. Now, anything to the first power really doesn't do anything, so it's just the same as 0.5 times a half, which means 0.25. And, molarity per second. And the second one is very similar, 0.5 times a fourth to the first. It's 0.5 times a fourth, 0.125. So if this was second order, this would have been 1/4 squared, which would be 1/16, I think. So there you go. That's just a little bit of practice. In our next video, we'll talk about finding and determining rate laws. But for now, hopefully you at least have an idea of how they work. Thanks for watching.